nice lunch break. So we are very happy about having Nicky Gilbertus today giving the next talk. So he's a group leader at the Helmont AI Institute in Munich, where he's working in machine learning and causal machine learning. So the title of the talk is going to be a class of algorithms for general instrumental variable models. And the title already looks more exciting, so I can't wait to see what is about to come here. So welcome, Nicky.
Awesome. Thanks for the invitation. So after the great introductory talks in the morning by Ricardo and others, this is going to be more on a sort of what does a hands-on project in causality look like or could look like. So this is also joint work with Ricardo. And as a shameless plug, I just recently joined Helmholtz AI in Munich, and I'm still looking for PhD students and postdocs, both at Helmholtz AI and also at TU Munich. So if you find any of this interesting, please just shoot me an email and I'm happy to discuss. So I'm also going to start with some motivation. This is now something we've already seen throughout the day, but I think it's worth recapping. So in the early 1950s, I'm going back to lung cancer and smoking. So the first half of the 20th century, I should say, people saw a steep increase in lung cancer cases and death due to lung cancer, at least in Western civilization. And at the same time, people started to smoke a lot. So that already seems like, two things going up at the same time. We've now seen this before. It doesn't need to be causation. So at the same time, traffic really increased. Industrial revolution was going forward, or there was more industrialization, so more exhaust fumes from both cars and industry, and also people were just moving closer together, so there was a higher density of population. So it could have been all these things. And the question, of course, that we would want to answer in causal inference is what is actually going on. And at the time there was, a lot of researchers investigated specifically the relation between smoking and lung cancer, and there was a lot of correlation, to say the least. So I'm not going to go through all these details here, but people did all kinds of correlational studies, and it definitely didn't look good for smoking. And there was even sort of semi-experiments where people would just survey 30,000 doctors out of the blue and then just wait and see who dies first. So that is already more getting towards an actual cause effect, but still not hard evidence in that sense. So due to all this correlation, the British Medical Journal actually came to this very careful conclusion that the most reasonable interpretation is direct cause and effect. You can see this is still very carefully worded because people simply didn't know. And in particular, there was this gentleman, Fisher, that we've also heard of before today, who was a very renowned, or is still a very renowned statistician, and also was an avid smoker. So he said, really, you can't know, just wait a second here. We're seeing these two things move together, smoking and lung cancer. And of course, you could come to the conclusion that smoking somewhat causes this, but there could always be the scenario where there's some unknown, unmeasured factor that causes both. So maybe there's some genetic variation that makes people experience nicotine differently, or just have a better taste for cigarettes, and at the same time gives them a predisposition for lung cancer. And he said, then people, of course, started looking for such things and didn't find any. But even more than the specific genetic effect, there could be any kind of environmental factors. There could be anything out there that we haven't measured, that we haven't looked at, that just causes both things. And that would explain equally well this correlation that we're seeing. So in this setup, we will call the smoking a treatment. It's not like a treatment in a clinical sense, but in terms of the causal relations, we are interested in what happens if smoking is our treatment and we want to look at lung cancer as the outcome, for example. Then these other factors we would call confounders, and in this specific case, we're calling them unobserved confounding. So something we may not know about that causes both things. And the issue here is what we have seen already in the morning, is that we can't identify the treatment effect of smoking on lung cancer if there is such unobserved confounding. And this is the issue we want to deal with in this talk. So to set the stage a bit more formally, or more from a machine learning perspective, I want you to look at this point, this data set. Let's say we've recorded some real valued X and some real valued Y, and these are the data points we have taken. So as a good machine learning student, you immediately know what to do. You fit a line through here. And if I asked you, what if x increases, how does y change? You would say, well, y is going down as x increases. So to make this a bit more formal, what we're doing here is we're saying we think that y is a function of x. And here I'm making this assumption that y is just a deterministic function of x, and then there is some additive noise term. And then if we also assume, so this is now an additional assumption, that this additive noise term conditioned on x has 0 mean. So this is just this sentence here, the statement here is that the expectation of the noise at a given value of x is 0. Then we can do the following. We can plug this in here. So we just use this equation. So here it's nothing but the expectation of the noise given x, and we know that's 0. So if we then regroup everything, we find that we can get the functional form of how y depends on x. This is what we want to get at. We want to make a statement of the form, what happens to y if I change x? And we can just get it by the conditional expectation. So then before I can even say causality, people pull out some linear regression, do a least squared fit. And what we get is this line. And the negative slope of this line also indicates that as x goes up, y goes down. So far, so good. That is what we would do in standard function fitting. And the key assumptions I've made here is this additive noise plus the 0 conditional mean of this noise. So now let's look at what could also happen if maybe these assumptions do not hold. So again, I'm showing the same data, but now someone comes to you and is like, oh, actually, I've measured a third variable here. It's not just x and y. I've also measured some c. So we can also look at the scatter plots of c with x and c with y. And here we see that if c goes up, then x goes up. And if c goes up, y goes down. So now you're thinking, maybe what I'm looking at here is actually just c changing, and it makes x go up while y is going down as I increase c. So we're in this graph that we had before, sort of x on y and some unobserved confounding, it could be a situation like this. So here now I call it explicitly a confounder, and then there are some independent noises for x and y. And this is actually how this data was generated. It's also in the previous plot. What I did was I sampled some c and some independent noise x, and then x is just a linear function of the confounding, and y is a linear function of x and the confounding plus again some noise. So in this example, these two are just independent Gaussian noise variables. So what happens now is if we want to know the effect of x on y, so the question, what happens to y if x changes, becomes a bit ambiguous, right? You can say, do I only care about this? And now we already know what this is, the intervention. So when I fix x externally, how does it affect y? And here we can see it's actually just directly proportional. So it's linear in x with a prefactor of 1 here. So what you would expect is that if you change x, y should be going up with the same slope, right? Of course, the reason why the data looks like this is because x and y both are affected by this confounding factor. So if we again look at the two conditions we had before, and we try to sort of match it with our current process, then f of x would just be this x. So that is how y depends on x only. But now, instead of the single additive noise term, we have this whole thing here. So there is also an independent noise, but there's also this confounding c. And now we can see that this assumption that we had before doesn't hold anymore. So if we look at this entire blue term conditioned on x, then the mean is not 0 because x also depends on the c here. And that means that we cannot actually get at f of x by computing the expectation of f of y given x, but we want to compute y given do x. By that, we can recover how y actually depends on x in this functional form. So here, the true causal effect, so that would be the functional form of this dependence, is just the linear line x. And you can see that it can actually be quite misleading just looking at the data, because clearly you would say, well, y is going down as x increases. But the causal effect of x and y is actually increasing. So it can really differ starkly from what you would expect by just looking at the observed data. And now you may say, well, if data doesn't tell me anything anymore, then we might be losing hope, right? If I look at this, the data, another data set, I might be saying, well, very obviously, if I want to predict y for x, then I just fit this polynomial maybe. and it looks like a pretty good fit for the data. But again, what I've done here is that there's some confounding in the data generating mechanism, and the causal effect of x and y is actually an upward shaped polynomial. So again, quite unintuitively. So the question is, what can we do, right? Does this mean that anytime I want to say something about an interventional question or a treatment effect, there could always be these things lurking, right? There's always a billion things I haven't measured that could give rise to a completely different cause effect. And in this general case, we actually cannot identify the causal effect, but people have found ways in which it's possible. And one super common situation or tool is instrumental variables. So all that means for our purposes today is that we assume that we have measured another variable. So by the way, the solid circles mean that these variables are observed, and the dotted one is unobserved, assumed to be unobserved. So if we have this additional variable pointing into x that satisfies a few conditions, then we can sometimes identify this causal effect. So here, terminology again, x is the treatment, y is the outcome, set we now call an instrument, and we have the unobserved confounding here. So the requirements that we need for set, this instrumental variable, look a bit obscure, but hopefully they're understandable. We want set to have an impact on x. So we want that x actually depends on set, as indicated by this arrow. At the same time, we want set to be independent of u. So this means that set is not also just part of this whole confounded thing. So otherwise we couldn't say anything again. So this is actually a pretty strong assumption, saying that the instrument is now independent of these potential unobserved confounders. And if you look at the econ literature, then people will spend whole papers on trying to justify this assumption. And also the third assumption is that set only influences y via x. So there is no, for example, direct arrow from set to y, but actually all the influence goes through the treatment x.
Cool. That's a quick question.
Mm-hmm.
Someone says, can we assume that if it's unobserved confounding, that means it's a latent variable? Is that the same? Is that the same thing, or is that a different? Is that like the same terminology, or is that different?
I think that's slightly different terminology. It's just like structural causal models are, in a sense, more specific than just general probabilistic models. In practice, I think terminology may mix a little bit. And if you want to model these kind of things, you may well speak about an unobserved variable as a latent variable. But I think it's just coming from two different fields in terms of terminology. Yeah.
Cool. Hope that helped.
So, right. So the last assumption is that, that we just had that set is independent of y given x and u. So x sort of conveys all the information from set to y. And now if we again have the assumption that we had before, that y is sort of some deterministic function of x plus some additive thing. So in particular, the effect of u would be in here. Then now we only need this weaker assumption. Remember before we had to ask that the expectation of the error term conditioned on x is 0. And now we just say that the marginal expectation is 0. So if we have that, then we can do a simple calculation. We start with the expectation of y given set, so at a specific value of set. And we just plug in our assumption for the functional form of y. And we make use of this condition and of the assumptions we had for an instrumental variable, and we arrive at this reduces to just the expectation of f of x given set. And here I just wrote this out as an integral. So what we can see here now is that the expectation of y given set is identifiable from data. So this is something we can actually compute, right? If you have a table of data with x, y set entries, you can look at a given set, what is the expectation of y, either by binning the data or whatever have you. And the same holds true for the distribution of x given set. So this is also something we can just look at from the data, so to speak. And that means that if we look at the very left and the very right, we have this integral equation for f of x. And this is what we wanted to get at, right? We want to get at the functional relation of how y depends on x. And under some fairly mild conditions, this integral equation has a solution, and it's also unique. So then we can actually identify the causal effect, the average causal effect. And
cool. I've got a quick question on that as well. So Rubo says, how can we deal with the case that we don't know the functional form? Okay, so I think it shouldn't matter, but yeah. Suppose that we do not know the functional form. It seems that when using the wrong model, the residual could also not be an independent noise, though there is there is no unknown confounder. Does that make sense?
Yeah, I think so. So probably that's two parts. If we stick to this assumption, so that there is just a function of x plus the noise, then we do not know this functional form. This is what we want to identify here, this f of x. Of course, if you're asking about this larger functional form, why is y not just a function of x and some error term? This is exactly what we're going to get to. So these assumptions are, yeah, pretty strong assumptions, like just assuming this additive noise. Mostly people are doing this because it does allow us to do computations, but there is no good reason for why this should ever hold true in practice, I think.
Cool. I think this is an important point, though. Maybe, Rubo, is that clearer? Do you want to, you should be able to reply. Mm-hmm. Are you there? Hopefully, or maybe not. Okay.
Yeah, just jump in again if it's not.
Oh, well, if you,
so next slide should clarify a few things.
Grand. Okay, that's fantastic. Thanks.
Not this, after the example, we'll see more about this. Okay. So now I'm going to show a brief example. This is a very common technique in econ and other fields on using causal inference to compute the causal effect if we have this instrumental variable set up, and it's called two-stage least squares. So we make all these assumptions, we assume this all holds, and in addition, we assume that all functional relations here are linear. So it's even stronger assumption for this specific technique, just to see how that could work. So again, we look at the data points from before, and now I'm adding this instrumental variable. Now this is not the confounder. Remember, there is also confounding in this case, but now we assume we also have this instrument that satisfies the assumptions from before. So the instrument affects x, and through x, it also affects y. So we see a slight dependence here. So what we do in the first stage of this two-stage least squares is that we fit a least squares linear fit to set on x. So this is now trying to predict x given the instrument. And then in the original data, we sort of replace all the true x values with the ones predicted from this line. So currently we see x values reach from -3 to 3 roughly, but the predictions from set only go from -0.5 to 0.5 or something. So this is now this plot where instead of the true x's, I plot the predicted x hats by this purple line. And now I fit another, this is now the second stage, another line through this data. So not just y on x, but y on the predicted x if I'm using set to predict x's. Now I'm zooming out again. The purple points here are the exact same points that we saw on the previous slide, and the line is still the same line. This is also an interesting counterintuitive thing. If you wanted to fit the least squares line through these points, you probably wouldn't guess that it's this one, but that's actually the least squares fit for the purple points. And now we see that if we look at the entire data again in gray, so x and y values, that the second stage of this procedure that is supposed to give us the causal effect of x and y is not aligned with the data at all, as it shouldn't be. So the red line is the true causal effect from the data generative model that I've used, and it's already quite close. And if we had more data, then it would actually converge to this thing. So this is one procedure under a lot of assumptions, additivity, linearity, and the assumptions for the instrument that gives us a true causal effect in this situation. So now we come to our problem formulation, which is exactly this scenario. So we have the same assumption on the graph. We have an instrument, treatment, and outcome. We now want to allow for any kind of function here. So x should be allowed to be any function of set and u, and y should be allowed to be any function of u and x. And that could be nonlinear and in particular non-additive. So now we're getting rid of these functional assumptions. And this has been for the most time in causal inference, this one size fits all assumption. Let's just assume there's additive noise because then we can do things, but no one really questioned this assumption. So this is what we want to do here.
Cool. Really quickly, that feels like it touches on another question. How does this relate to heteroscedastic noise? Does heteroscedastic noise imply there is an unobserved confounder? So maybe that relates to this additive question as well, maybe. I don't know.
Yeah, I guess it depends on in what context we're talking about heteroscedastic noise, but that could be something that comes about through unobserved confounding. So certainly this model has the capacity to model heteroscedastic noise, whereas the very original assumption doesn't really, right? So if you assume that the mean of the error given X is always 0, then at least you're restricting what kind of noise models you can have and what kind of heteroscedasticity. Difficult.
Yeah, I hate that word.
Yeah.
Cool. And there's another question, unfortunately anonymous, so I can't unmute them, but sorry, what do you mean by additive in this context?
Oh, so additive is the fact that here I said that y is a function of only x, and then there's just a plus term for everything else. So this is additive. What we're looking at now is where the noise term can also be sort of an argument to the function. So that means there could be a term like x times the noise, or x to the power of the noise, or the sine of x times y of the noise. Yeah. So it literally just means that there's a function with a single argument for x, and then everything else is just an additive term on top.
Right, yeah.
Yeah. And this allows us to essentially, why we need this is so that we can exploit linearity of expectation here when we want to identify the causal effect.
Yeah.
So now we assume this, we don't have this.
Yeah. Okay. Thank you.
If we allow for these more complex models, then we actually cannot get at the causal effect anymore. So we only get partial identification, which means that we can only compute bounds on the causal effect. So remember, what we want is sort of the average causal effect, which is the expectation of y given do x at a specific value x star, at a specific treatment value. And we can't compute that exactly anymore, but we are trying to get the lower and upper bound. So that may already help. For example, if we can say the causal effect is at least 0.5 and at most 2, then we at least already know the sign. Okay, so the general problem formulation for us now is the green variables are things that we have observed, x, y, and z. And then there are these unknown functions g and f for the two variables x and y. And also this completely unknown noise distribution. So u could be a high dimensional weird distribution of things that we haven't observed. So what we want to do is optimize over these unknown things, over the functions g and f, and over the distribution u. So the goal then is to look at all possible combinations of functions g and f and all possible distributions over unobserved variables, and such that these combinations reproduce the data, right? We are given some data, and we want to make sure that the g and u we plug in actually satisfy these two things. So they reproduce the data we have observed for x, y, and z. And among those models, we want to find the maximum and minimum expected outcomes under intervention. So now that sounds super difficult, right? We want to optimize over all functions, whatever that means, and all distributions. So the rest of the talk is mostly going to be trying to restrict that a little bit and operationalizing that optimization. A few remarks on this from the theory side. So if we do not put any restrictions on g, f, and u, so if we literally look at all functions and all distributions, then all bounds become vacuous. So then, bounds are always minus infinity and infinity. So then we cannot identify the average treatment effect. But under fairly mild assumptions, and this is also fairly recent results, for example, if the functions f and g are assumed to have a finite number of discontinuities, which is a fairly general assumption, then we can get non-trivial bounds on the treatment effect. And yeah, the rest of the talk is going to be trying to operationalize this optimization, so it's less theoretical and more practical engineering thing in a sense. Okay, so what we need to do is we need to find convenient representations of these unobserved confounding distributions, and ideally we want to be able to sample from it, and even more ideally in a differentiable fashion, so we can optimize through it. And we also want to find convenient function spaces that we can parameterize in a nice way. And of course, on top of that, if we have our family of distributions, our family of functions, then we need a way of figuring out which ones reproduce the data we have observed. So to reproduce the data we have observed, it actually suffices to preserve the marginal x given set and y given set. Okay, so our approach here is to use an idea by Balke and Pearl from '94, the framework of response functions. And what this means is that if we look at this whole situation with the functions f, g, and the distribution u, then what we really care about in the end is how y depends on x in this functional form. And what we can do is that as soon as we fix a value of u, then we can say, y has two arguments, u and x. If u is fixed, then it becomes only a function of x. And the idea is now to collect all possible settings of u that give rise to the same function y of x. So an example will make this more clear, I think. So assume that the true functional form of y, it still has two arguments, x and u, is of this form. So it's nonlinear, we have this multiplicative term, and non-additive. So here, I can't just write it as a function of x plus something because of this interaction term. But as soon as I fix the values for u, so let's assume now u1 takes the value 1 and u2 takes the value 0. So here I'm assuming a two-dimensional unobserved distribution, but that could be higher dimensional. Then I'm ending up with the function only of x. So now what I'm doing here is I'm giving this setting of the u variables an index r. So that is just an alias for whatever that setting of u is. And I'm saying now I have a function of only one variable for the function f of r. So once the values for u are fixed by this alias, then it's just a function of x, namely this one. So I'm trying to hide this interplay of distributions over u and functions f into just a distribution over functions. This is the idea here. So instead of a potentially multivariate distribution over u and some function family f, I can just put all of that into a single distribution over functions that are function of a single variable, namely for y given x. So graphically, I can sort of say this whole u setting is collapsed into this index set r. So it could be that here two different values of u still give rise to the same function. So it's not the case in this example, but that could also happen. So I'm collecting all these u settings that give rise to the same response function down here. And now instead of having to optimize over the distribution and different functions, I only optimize over this distribution over functions directly. So that also reduces our problem of sort of choosing a convenient function space and finding a convenient representation of u to just finding a convenient representation of a distribution over functions. So for the response functions, we now need to make some concrete assumptions. Namely, first, we say we use a parametric form for these functions. So we have some k-dimensional real parameter that tells us what the response function is. So now instead of f sub r, where r fixes this value of u that gives rise to one-dimensional function, we subscript it by the parameter theta. And for simplicity, for the optimization, we only work with linear combination of nonlinear basis functions. So this is quite restrictive, I admit, but still, if you have a rich set of nonlinear basis functions, then of course a linear combination of them can be quite powerful if we think of Fourier series or other kinds of polynomial series. And these will be our response functions. And we in practice for these nonlinear basis functions, we will use low dimensional polynomials or low degree polynomials, but also neural networks and Gaussian processes. So there's some Gaussian processes in there as well. So what we have now is that for a single parameter setting, we have one function just from x to y. But as we've said, we want to deal with a distribution over functions. So we now need a distribution over these parameter vectors, which then gives us a distribution over possible response functions. So here you can now actually think of, these are all the possibilities of how y could depend on x. This is what we want to figure out, right? How the outcome or the average outcome at a given x. And we need to average sort of over all the functions, over all the parameter settings of f theta that are compatible with the data. Okay, so now we need to deal with how do we optimize this distribution over functions. So in our case, it's just this distribution over the parameters. Well, each such distribution does imply a full causal model that now contains everything. This was sort of collapsing this U into this R thing, which is now in the distribution over parameters. And our goal is now to optimize over these distributions. And this is the, so we want to optimize over these distributions such that we still reproduce the observed data. So we need to match the marginals X given Z and Y given Z. And we can compute them now with as soon as we have chosen this distribution by this integral. So in order to be able to evaluate all of that, we also parameterize the distribution over thetas. So now we have another parameter eta that parameterizes our thetas. So to recap, there's sort of now nested parameterization. Each f sub theta is one response function. A distribution over the thetas gives us a distribution over response functions. And this distribution is now parameterized by eta. Okay, so, and now this in the end are the parameters that we want to optimize over, these etas that tell us what the distribution over response functions look like. And ideally, we want to get sort of a low variance Monte Carlo gradient estimation for this thing, and also want it to be differentiable in sampling. So overview again, we have the objective of computing the average treatment effect, upper and lower bounding it with over these distribution of response functions. So now everything has been collapsed into this distribution here. And at the same time, the constraints are that we match the observed marginals. And this is now we have found sort of how to parameterize this whole thing. Now we need to describe how we can match the constraints that we match the marginals that we have observed. So first we need to match X given Z, sort of the treatment conditioned on the instrument. And also we need to enforce that C is independent of U. That was one of the conditions for instrumental variables. And this is something that our model also needs to respect. And what we do here, we first factorize the distribution of X and theta given Z in this way. And now look at the two factors individually. P of X given Z is something identified from data. This is what we've also seen in the very beginning. This is literally just looking at all the X values you have for a specific Z value in your data so that we can identify. And for the second factor, we had to get a bit creative. Namely, we chose a copula density for this factor, which has a number of advantages. So first, we can plug in the univariate CDFs of X given Z and all the thetas. And thereby, we can ensure that Z is independent of U. So the U, the confounder, is now in the thetas. These are the response functions. So this is all poured in here. And we can make the X given Z a separate argument to these things from the other CDFs. And then we still need to define the marginalities. And here we just assume Gaussian densities for the marginals of the components of the thetas. So this is now a multivariate Gaussian copula. And the advantage we have here is that it's fairly easy to sample, and it automatically enforces both Z independent of U. And we can here just plug in the empirical distribution, a cumulative distribution function of X given Z. Again, this is identified, so we can just hard code that in, and we automatically match, or our sampling procedure already guarantees that we're matching the observed marginal X given Z, the observed conditional X given Z. So for the multivariate Gaussian copula, the parameters that we are then left with are the means and variances. So this is something we can optimize over in our procedure for the different parameter entries for the response functions. And also in the copula density, there is still a correlation between all these factors, a correlation matrix or covariance matrix. And this one we encode by just the Cholesky factor L. So now these are just individual means and variances. We're taking logs, so they stay positive. And then there's this Cholesky factor L that we optimize over. Now, the second constraint for matching the data, the observed data, is that we match them P of Y given Z. And if we write that out just in terms of probabilities, then we want for all Ys and all Zs for that equation to hold. So this is something we can look at from the data. This is again, just a look at the probability of y being smaller than some value at a given set. And this is what's entailed by the model. This is now our model and distribution at a fixed eta for this probability. And the issue with trying to satisfy that constraint is that it's an infinite number of constraints, sort of for all y and all z. And also there is this nasty integral over a non-continuous indicator function. So this one also causes issues in practice if you want to differentiate through. So what we do is we just take a crude approximation of all of this. Namely, we choose a discrete grid in set values. So instead of looking at all set, we just look at a finite set of these values. And we choose them sort of homogeneously in the CDF space. So this capital F subset is the cumulative distribution function of set, the empirical one. And we just choose the inverse and use a homogeneous grid. So if these are all the set values, so there's just set on the set axis, and then this is the empirical cumulative distribution function of all these values. Then what we do is we take a homogeneous grid on this 0 to 1 range and look sort of where it hits the cumulative distribution function. And then all these vertical dashed blue lines, those will be our set M's. And then we take all the data points and we assign them to the nearest bin. So we just take all these points belong to this bin and these points belong to this bin. And thereby, in this example, we bin the data points into 20 bins. And then instead of the probability of y smaller than y, we choose a finite dictionary of basis function and ask the expectation of those to be preserved in our model. So this, instead of the probability here, we take the expectation over a bunch of functions at a given bin, at a given set point, and this is the equivalent in our model. And these are now things, if the phi's are nicely behaved functions, then we can actually evaluate that. So again, this is something we compute from data. Here, we literally just look at the first and second moments. So we only use expectation and variance. And what it means is literally here, it's the same data points. I've colored them according to which bins they're in, but I'm also showing their y values. So what we're doing is I take all these data points, I compute their mean and their variance in the y direction. And this is one term that I want to satisfy in the constraints of my model. So here are all the different means of these 20 bins, and the blue shaded region shows their variance. So this is just saying I want my model to reproduce the marginal of y given set.
Cool. There's one quick question. It's about how to approximate the integral. Can we use Bayesian quadrature to approximate that integral? I guess? Yeah,
so essentially we're gonna use Monte Carlo estimation for computing these integrals. So this is our copula density, the p sub eta, and we can fairly easily sample from the copula, and by using some reparameterization tricks, we can even sample through it in a differentiable fashion with respect to eta. So yeah, we just take a sample of this thing, and then our response functions have to be fixed up front. Let's say these are polynomials. We just plug in all the x's we get from our batch, and then the dictionary functions here are also fixed. So then we can just average to get an approximation for this integral.
Cool. Hopefully that answered the question. There's another question as well. Oh, I see. Okay, maybe this is towards the end, but okay, I'll ask it now as I've started. Is there an implementation available either in R or Python or something? So sorry, that was a question for the end of the talk probably, but as we've got to it.
It's not yet on GitHub, but I'm working on cleaning it up at the moment, and it will be there soon. So cool. there's an implementation in Python. We did all of this in Python.
Fantastic, good choice. Yeah. Okay, so I'll let you get back on top.
Cool. Okay, so now we can go back to our current overview. This is our objective, the expectation of y given do x star, and we want to minimize and maximize over all possible distributions that give us a model that is compatible with data. So this means that we match these marginals. The p of x given set is included by the copula approach that we chose for this p sub eta, so for the distribution. That's something we can just fix from the observed data. And it also automatically implies that set is independent of theta, which just means set independent of u as we had before. And this other one is fixed by an explicit constraint. So we actually just wrote it out, and we just have to add that as a constraint to our optimization. So the final procedure that we have is, again, the objective. We've seen that. And I split the constraint in its left-hand side and its right-hand side. And okay, so we start with the green parts, these are things that we have to choose up front. We have to choose how many of these bin points we choose for binning up the set values. So in the example before, I think it was 20. We have to choose how many of these dictionary functions we use to enforce the constraint that P of y given set matches the data. In our case, that is just 2 for the mean and variance. So these dictionary functions here are also just identity and squared for mean and variance, just first and second moments. And we have to choose our response function family. So here we have to choose, for example, we use linear combinations of polynomials up to degree 4 or something like that. And all of this is just evaluated at a single treatment value. So if I want this whole line of how the expectation of y given do x for different x's, then I actually have to repeat this whole optimization at different x stars. So this is sort of what we fix up front. Then the left-hand side, we can compute from data. As soon as I get my data points, I do this binning procedure, and then I just compute, means and variances for this point cloud, as I've shown in this one plot. So then the left-hand sides are fixed. And we have our copula from which we can sample x and theta values. So this is how we are going to evaluate both the objective by just sampling a batch of theta values, computing this integral. All the other things are fixed by just averaging Monte Carlo approximation, and the same for the constraint. So then we want the right-hand side to be as close as possible to the left-hand side to satisfy the second constraint. And in practice, we give that some slack. So we don't, we just say if it's close enough, either in absolute or relative error, then we're going to be happy. For the actual optimization, we just use augmented Lagrangian. So we have the optimization and we latch on a Lagrangian multiplier plus the square difference of the left-hand side and the right-hand side. And then we push everything through automated differentiation to optimize over eta. And yeah, that is essentially all there is to it. So we sample for each of the grid points a batch of theta, evaluate the integrals. And overall, you see that the constraint has 2 subscripts. So if this is 20 and this is 2, then we have about 40 constraints. So it's a fairly large number of constraints for this optimization. And yeah, then we use checks in this example for auto differentiation and get the gradients and then just use SGD. So this is non-convex. We have no optimality guarantees in the global sense, but locally we find fairly good results. Again, still got a little bit of time.
Yeah, 5
I'll get to some empirical results as well. So one thing I haven't yet described a lot is the choice of basis functions. So this is roughly saying what kind of functions am I allowing as causal effects? So how is y allowed to depend on x? So that clearly is an important point and says a lot about what degree of flexibility we're allowing here. So the simplest thing we experiment with is just polynomials. So we literally say, it's just some theta 1 as a constant plus theta 2 times x plus theta 3 times x squared and so on. And usually we here actually stop at either linear, quadratic, cubic, or quartic. So we don't go to high degree polynomials. Then another thing we can use for more flexibility is a neural network. So what that means is that we fit a small MLP, a fully connected network, to just the observed data. So just from x to y. This is just from a single real value to another one. And then we cut off the last layer, so to speak, and look at the activations in the second to last layer. And we use those as our psi k. Second. Yeah. Okay. We have some room management system here that doesn't always quite work. Okay, so I take the activations of the second to last layer and then linearly combine them. I know that one of those linear combinations reproduces the observed x and y given x. And the hope here is that the true causal effect can be expressed within similar functional form. So I can take all kinds of linear combinations of the activations to get at the true causal functional form. And the similar idea is to just do a similar thing with Gaussian processes. So train GPs on just x to y, so just real valued function here, a scalar real valued function, and then pick a few random samples from that GP and use that as nonlinear basis functions. So again, it's the assumption here is that the observed functional form between x and y is expressible within the same realm of, or the causal effect is expressible in the same realm of functional forms than the observed distribution. Okay, here are now some examples. These graphs are pretty loaded, but maybe you can look at them in peace afterwards. So the gray dots are the data points. This is the example we have seen in the very beginning already. Then I'm showing the true causal effect. So this is expectation of y given do x star is the red line. So this is also as before. No, I've shown you this. It's counterintuitively not following the data points, but this is the true causal effect. Then this dashed Ceon line is two-stage least squares. And for now, let's ignore the purple one. This is akin, it's kernel instrumental variable regression. It's akin to two-stage least squares, but doing kernel regression instead of linear regression. And then what we want to highlight are the blue and the orange ones. These are the lower and upper bounds that we compute with our techniques. So what we can see here is that in this linear setting, so this is fully linear Gaussian setting, it satisfies all the assumptions for two-stage least squares. So it has additive noise and it's just linear. So two-stage least squares just nails it completely. It gets the effect completely right because all the assumptions are satisfied. Now, what we are saying, if these assumptions are not satisfied and we are using linear response functions, so that means we don't assume additivity. Two-stage least squares always assumes additivity, and in this case it does because it happens to satisfy additivity in the way I set up the data generating process. But you can see that our bounds still capture the true causal effect. So the true causal effect is within the bounds, and in most parts of the X range, they also give a pretty good estimation of it, right? So here you could say even on the edges, we still get the sign correctly. So we still know that the causal effect is positive, even though it could be anywhere in between here. So now what we also show are these thin lines, and these are other possible models that could have generated the data. So what we do here is that we fit a latent variable model, a variational autoencoder, and try to generate the data points in sort of this generative fashion with different random initializations. So here we're producing a lot of models that could have equally well produced this data under the unobserved confounding setup. And we see that there is actually a lot of models that could have generated this data that don't have the same causal effect than the true one that we're looking in. And crucially, all of those still lie within our bounds. So that means that, and pretty tightly, so our bounds pretty well capture what could have been generating this data. So it allows for all the possibilities here. And this is where we are assuming that the response functions can only be linear. So it's quite restrictive. If we now, in the same setting, allow for quadratic response functions, then our bounds become much, much looser. And this is also expected. So if we allow for more flexibility, then there's just many more possibilities of having generative models that give rise to this data, but have very different causal effects. In particular, again, these black lines now in our latent variable model allowing for quadratic causal effects, we see that there's actually a lot of models that have these weird causal effects along these lines that are, not on the true causal effect, but could have generated the data. And again, they all lie within our bounds. So now they're getting quite loose. And if we allow for this neural network response functions, then at some parts they become even looser. And also there's now a lot of possible causal effects that could have generated this data. Okay, so then we have a second setting, again, linear Gaussian, but with weaker confounding. So now the instrument has a very strong effect and the confounding is fairly weak. And here we see that our bounds become even better. So now we almost nailed the causal effect. So there's not much variation, not much room for other models that could have generated this data anymore. Similarly in the quadratic setting and also in the MLP setting. Okay, of course, now still have a little, I'm almost out of time. So this is the last slide.
Yeah, sure.
So now if we go to a non-additive setting, this is where things get interesting, right? So if we don't assume this whole additivity and linearity, but we have this quadratic setting that I also showed in the beginning, then if we assume linear response functions, so again, the red line is the true causal effect. Here now, two-stage least squares doesn't do anything because all its assumptions are violated. It can't deal with nonlinear things. So this is why these lines are just flat. So we can ignore them. And here it seems that our bounds are also wrong, right? The true causal effect is outside the upper bound. But what is going on here is that we have assumed, or we have put in as an assumption, that the response function can only be linear. So that means that we are only capturing effects where linear response functions could have given rise to the data. And all these thin black lines, so models that could have potentially generated this data under linear cause effect relationships, are actually within our bounds. So this is just because we have made false assumptions about the underlying process. But within those assumptions, the bounds would have worked. As soon as we now allow for quadratic response functions, bounds become much looser again. There's a lot of possible models that could have generated the data, and we essentially capture them within our bounds. And now the true effect is also essentially within the bounds. And this is MLP models, so similar thing as we've seen for the quadratic one. And then again, a related setting where the confounding is a bit weaker and the instrument is stronger. And here, the model even recognizes that within linear response functions, we just cannot explain this data. So if there is no bounds drawn, that means we cannot satisfy the constraints, and the constraints were, matching the observed data. So if there's not so much room for confounding, then here our technique actually says, well, I don't find any model that could have plausibly generated this data with a linear response. So I'm not going to give you any bounds if you want to make that assumption. As soon as we allow for quadratic responses, we capture the effect pretty well and fairly tightly, and similarly for MLP response functions. There are some more experiments and other underlying ground truth data that we've used in the paper that you can look at in the link. And with that, I want to thank you for your attention, and I'm open to more questions.
Cool, thanks for that. That's amazing. There's quite a few questions in the chat and in online, but I think we're out of time for that. Maybe people can ask them in the discussion afterwards. Will you be around for the? Yeah, brilliant. Okay,
yeah,
cool.
I'll be around. So happy to take more questions then. Maybe I can already go through them in the chat now.
Yeah, okay. Yeah, it's a bit awkward because people can't reply on the thing, but you're welcome to try. You can write text responses, I guess, to them there. I'm just aware of needing to get to the next speaker, but I think the problem is it's too interesting, so there's too much to talk about. Cool. Okay, thanks again. That's fantastic. I was thinking maybe could we have a 2-minute break for everyone before Virginia starts her talk? Would that be okay? Cool. Okay, so if everyone wants to sort of reconvene in 90 seconds for the next speaker, that would be fantastic. Cool. Thank you again, Nikki. That was amazing, really interesting stuff.
Thank you.
Cool. Thank you.